Today we will bring you a new paper, a meso-to-macro cross-resolution performance approach for connecting polynomial arrival Q model to volume delay function within flow demand to capacity ratio. This article was written by Xuesong Simon Zhou. Although the macroscopic volume delay function has been widely used in static traffic assignment for transportation planning, the planning community has long recognized its deficiencies as a static function in capturing traffic flow dynamics in Q evolution process. In the existing literature, many queuing-based and simulation-based dynamic traffic assignment models involving various traffic flow parameters have been proposed to capture traffic system dynamics on different spatial scales. However, how to calibrate these DTA models could still be a challenging task in its own right, especially for real-world congested networks with complex traffic dynamics. By extending the fluid-based polynomial arrival Q model with quadratic inflow rates proposed by Newell and cubic inflow rates by Cheng, this paper attempts to propose a cross-resolution queuing-based volume delay function to explicitly establish a coherent connection between the mesoscopic average travel delay performance function and a long-term planning horizon N. This paper develops a relationship from the macroscopic inflow demand to capacity ratio to the congestion duration of a bottleneck, from the congestion duration to the magnitude of speed reduction. The QVDF can be directly utilized to provide closed-form expressions for both average travel delay performance and the time-dependent speed profiles. The proposed cross-resolution QVDF provides a numerically reliable and theoretically rigorous performance function to characterize oversaturated bottlenecks at both macroscopic and mesoscopic scales. Next, I will introduce the major steps towards Q-oriented link performance function QVDF. Step 1 is that introduce a power function with oversaturation to duration elasticity parameter N to describe the relation between D/C ratio and P. This power function can be used to estimate P with D/C after calibration. Step 2 is that introduce a power function with duration to speed reduction elasticity parameter S to map congestion duration and speed reduction ratio. The ratio is defined by the cut-off speed flow, and the lowest speed Vt2, and Vt2 is directly related to the longest delay in the queue, as shown in Fig. 6. Vt2 and the longest waiting time Wt2 can be estimated with P via the calibrated power function. Step 3 is that with the cubic pack model, the inflow curvature gamma can be represented by P and Wt2 gamma then becomes a function of d/c. Step 4 is that derive both time-dependent Q length and average link performance during the congestion duration using the D/C ratio. Fig. 4 shows major steps to develop the QVDF, as well as other components. In this section, the paper conducts 2 case studies to evaluate the proposed QVDF. The first study utilizes the daily time-dependent time mean speed and link counts from 4 locations in a freeway corridor over an entire year. The locations are viewed as different modeling links. The second one considers a single oversaturated bottleneck on a 6-mile corridor and treats it as a whole modeling element or link with 4 months of sensor data. With these data sets, it is hoped to demonstrate how the time-dependent Q dynamics and time-dependent dependent speed profile estimation can be modeled consistently from the macroscopic link performance with the 2 studies through the following 2 stages. Fig. 8 shows the calibrated fundamental diagram along with observations for each link. The 4 fundamental diagrams have different patterns. Take link 137 for instance. Its calibrated capacity is 1,380.8 vehicles, r lane, which is lower than the other 3 links. The distributions of congestion duration, Q demand factor, D/C ratio, and inflow demand are plotted in Fig. 9. Fig. 10 shows the scatters and the calibrated curves between the D/C ratio and P for each link. Since each P corresponds to multiple D/C ratios with large disturbances, we calculate mean value of D/C C ratios for each congestion duration to ensure the exogeneity of D, C ratio over P in the calibration stage. Fig. 11 illustrates the scatters and the calibrated curves between the magnitude of the speed reduction and P. Similarly, each P has multiple speed reduction points with large disturbances. The mean value of speed reduction VCVVT21 for each P is used for the second step of calibration. Fig. 12 shows calibrated curves between D, C ratio and average speed within their congestion durations.